Hey guys, I want to talk about finding a limit of a function by using this method called direct substitution. If we look at this example right here, I want you to first of all remember what this is saying. What it is saying, what it's asking you to do is to find the limit of the function, which is this guy, as the x value approaches, or in other words, gets infinitely close to the value of 2. So let's take a look at what this thing looks like graphically. I can always come to some better understanding of what's going on by drawing a quick graph. So let's do that here. We've got 3x squared. I can make a quick graph by just plugging in some points. If x is a value of 0, 3 times 0 squared is going to equal 0. So I've got a point 0, 0. If x is equal to 1, 1 squared is 1, and 1 times 3 is 3. So I've got a point over 1 up 3. And let's just do one more point here. 2 squared is 4, 4 times 3 is 12. So over 2 up to 12. I know that this parabola will be symmetrical, so I'm going to just give myself the other half. So there we go. What I'm asking to find, or what I've been asked to find, is the limit as x approaches 2. So here's my x value of 2. What I want to look at is what's going on as I get infinitely close on my graph to where my x value is 2, which is this point right here. And again, I'm looking at what's going on as I get infinitely close from either direction. I've got to come from both directions and ask myself what happens, or what am I getting infinitely close to. And what you should notice on this graph is that because the point is defined on the function, or another way to say that is that my graph is continuous at this point. There's no gap. There's no discontinuity, there's no jump, there's no break, there's no hole. There is a continuous line going through the point of interest. And because that is the case, the limit is going to be the same as what the point actually is. We looked at an example just like that in the last video. So the point that I'm getting infinitely close to is 12. We can see that graphically. Hopefully that makes sense. But what I want to look at is a different approach to this, using this method called direct substitution. I want to emphasize this point. Direct substitution depends on continuity. This is a big deal. Using the method that I'm going to show you, called direct substitution, depends on if a function is continuous at a particular point. So looking back at the last example, or the only example, when I asked you to find the limit as x approaches 2 of the function 3x squared. Here's what we do. We ask ourselves, is the function continuous? Is this function continuous at this point? And if the answer is yes, which it was, I've already just shown you how it was, on the graph, the graph was continuous at that point, then what I can do is evaluate this limit simply by plugging the point in. So the point being 2, I'm going to plug that in as my value of x. So I get 3 times 2 squared. 2 squared is 4. 4 times 3 is 12, which of course is what we got when we approached this thing graphically. The only reason that we could do that on this example is because this function is continuous at this point. Using the method of direct substitution depends on continuity. If a function is not continuous, then we cannot use direct substitution. And this would be an example of that. The function here is 1 over x. I've drawn a nice graph of this. And if I try to find the limit as x approaches 0, at the point 0, we have to ask ourselves, is the function continuous? And the answer is clearly not. This function is discontinuous at 0. The graph disconnects. I can't draw this function without picking up the pen. So if I were to ask you to find the limit as x approaches 0 of the function 1 over x, you cannot use direct substitution, which interestingly, on this example, if you just took 0 and plugged it in for x, you would get a value of 1 divided by 0, which should raise a question, which we'll talk about later. So let's go ahead and formalize this observation into a theorem. We're going to have an if and then statement. The if part of this is that if the function f of x is continuous at some value a, then the conclusion of that is this: that the function evaluated at a will be the same as the limit of the function f of x as x approaches a. If some function is continuous at a particular point, which we're calling a, then the function evaluated at that particular point is the exact same as the limit as you get infinitely close to that point. Which just makes good sense. Hopefully that makes sense, right? Because you're saying as you get infinitely close to some point, all we're saying in layman's terms is that as we get infinitely close to this point right here, from both directions, it happens to be the same as what's actually going on at that point, because there's not a gap or discontinuity or a break or a hole. So let's wrap up with 3 quick examples here. We're going to go ahead and find these limits. For letter A, I'm asking you to find the limit as x approaches 2 when the function is 5. So this is kind of weird. Ask yourself, what does a function of 5 look like? Graphically, what is the graph of 5? This, remember, that's our f of x. So what I'm saying here is that f of x is equal to 5, or in other words, y is equal to 5. What is that line looking like? It is a flat horizontal line going through a y value of 5. So I first need to ask myself, is my function continuous at my point of interest? So if I go over here to x is equal to 2 and look at that point, I need to ask myself, is my function continuous there? And of course it is. This function is continuous everywhere. This function has no discontinuities or gaps or breaks or holes anywhere at all in its entire life. So of course at the point 2 it is continuous. So because it's continuous at that point, I get to use direct substitution. So this is kind of weird. I don't have an x value in this function. So where do I plug 2 in for x? Well, nowhere, because there is no x, right? So what is my answer? My answer is simply 5. The limit as x approaches 2 of 5 is 5. Or graphically, we should be able to make sense of this too. If I go from either direction and get infinitely close to my green dot, what does it look like I'm getting infinitely close to? It's still going to be the same height of 5. Let's look at letter B. Letter B, we've already just looked at this function. Looks like this. So first of all, I need to ask myself, is my function continuous? And this example I'm showing you because this brings up a good point. This function is clearly not continuous. We've already talked about that. I mentioned that. But what I need to ask is it continuous at a point? Our theorem says if our function f of x is continuous, not necessarily everywhere, but just at the point that we care about, at the value of a, then we can use direct substitution. So is my function continuous when x is equal to 4? The answer is yes. If I go over to 4, my function is continuous. There's not a gap there, there's not a hole there. So I can, in fact, use direct substitution. I can take 4 and plug it in for my value of x, and my answer is 1/4. Last but not least, the sine of x is the function. I'm trying to find the limit as x approaches 0 of the sine of x. So I've got to ask myself, is my function sine of x continuous at the point when x is equal to 0? And I happen to know, as you should also, having studied this curve before, that this is a continuous curve that has no gaps, breaks, or any kind of discontinuities, so it's continuous everywhere. For the entire domain, sine of x is continuous. So this allows me to use direct substitution and take 0 and plug it in for x, and my answer is the sine of 0, which is 0. So what happens if the value that we care about is not, or sorry, I said that wrong. What if the function is not continuous at the point that we care about? Then we've got to deal with our analysis a little bit differently, and we're going to look at that next.